I am Faisal Yaqub, and today we'll be learning about orthogonal trajectory differential equations. So, breaking up the name, orthogonal, what comes into your mind? 90 degrees, right? Or perpendicular. Trajectory, projectile motions, curves. So, I can say that we're talking about curves here. And differential equation leaves us with an equation which involves a derivative. Now, coming to the proper definition of orthogonal differential equations is that two family of curves that intersect each other at 90 degrees. Okay, two family of curves that intersect each other at 90 degrees. So there will be a bit of question or confusion in your mind that why am I using the word family of curves? Why am I not using two curves that intersect each other at 90 degrees? Well, there is a bit confusion in most of the people that what is family of curves and what is curves. So I'm just going to clear it out. Curve, and if we make a difference between the both, then we can say a curve is equation of curve is that in which there is no parameter or constant which may affect the equation somehow. And when we talk about family of curves, there is always a parameter or a constant which may affect it, and here it is k. So we can say that this equation is the subset of this equation when k is equal to 1, right? Now, coming to the relation of two slopes, two differentials when they are orthogonal to each other, so this relation comes into very handy that we will be using in our question. Now, coming to the method on how to solve a question when we are asked to find the orthogonal trajectory of an equation. We are given an equation which is y is equals to c sec x plus tan x. We are to find the orthogonal trajectory of this equation. Now let's start working. We were given y is equals to c sec x plus tan x. If we want to use that relation, which is m1 is equals to minus 1 upon m2, that means the negative reciprocal of the slope. So we might find first the differential of this equation, which will be something like this. Constant outside, d upon dx sec x plus c d. I have just separated the both terms, so don't be confused. Leave it with this thing. So we are left with this term d upon dx is equals to c d upon dx sec x plus c d upon dx tan x. Differentiating, we get c sec x tan x plus c sec square x. Now if we take common sec x and c outside, c sec x equation becomes tan x plus sec x would be equal to dy by dx. Now in this equation we cannot apply our relation of two slopes or two differentials, because here there is a parameter which may affect this equation somehow. So we will replace this parameter from our first query equation, which was y is equals to c sec x plus tan x. This was our first equation, y is equals to c sec x plus tan x. From this equation, c is equals to y upon sec x plus tan x. Now putting this equation into our recent equation, we get this: dy by dx is equals to y upon sec x plus tan x multiplied by sec x plus tan x. This will be cancelled out with this, and we are left with dy is equals to y sec x. Now this is our equation of differential. Now if we apply this thing, now this equation can be easily applied on this one. So to find the orthogonal trajectory of our equation will become the negative reciprocal of our differential. We will be using equation 2 from now on. Now dy by dx is equals to minus 1 upon y sec x. Now separating the variables, dy y is equals to minus 1 upon sec x dx. Integrating both sides, we get y square upon 2 is equals to minus sin x plus c. This is our equation, which is the orthogonal trajectory of our question. Thank you very much for watching my video. Feel free to ask any questions.